I'm a believer that perovskites will take over. And I think as an early innovator in the scaling, we have a place amongst that pantheon that'll eventually emerge. This segment of the industry is extremely dynamic, but we have to commercialize early, so we're ready for that type of scale production in the future.
This is EnergyCast, and I'm Jay Downhauer. Today we're talking about getting more solar energy with perovskites. You're forgiven if you're unfamiliar with them. They only started testing these in labs in 2009, but today they are starting to commercialize. My guest stands to be the first domestic manufacturer. Perovskites are considered thin film solar, much like cadmium telluride cells we discussed in episode 161. While you can produce perovskite-only cells, my guest says they plan to pursue a hybrid model using silicon modules. As he puts it, they'll, quote, borrow the outer glass, coat it with their perovskites, and then send it back for assembly. He says the benefit is that perovskites and silicon modules are best at absorbing complementary bands of the solar spectrum, so it's a good partnership. Perovskites have come a long way from the lab, and my guest says they've worked hard to overcome some of the technical challenges, namely the lifespan. This is organometallic chemistry. He says the earliest perovskites only lasted minutes. Now they've gotten it up to years, which is critical for cells that are expected to last at least 2 decades. The other issue is their metallic component is lead, and while the amount used in fabrication is minimal by the most conservative standards, it's still a PR issue. My guest believes these cells will one day take over silicon as the industry leader in solar technology. Right now, they hope the added perovskite performance they add to silicon modules is the first step in that journey. My guest today is Scott Graybeal, CEO of Caelux, a developer and soon-to-be manufacturer of perovskite solar cells based in Los Angeles. Caelux was founded in 2014. Scott joined the company in 2021. Last August, they made a major funding announcement that will chart their course towards fabrication. Scott and I also spoke a lot about the global solar market and what it means to produce solar cells here in the U.S. You might be surprised to find out just who can now be considered domestic. And we also take a clear-eyed look at what we're missing in order to, as I've been trying to understand over the years, what it takes for us to be able to build a single solar module soup to nuts. I hope you enjoy my conversation with Scott Graybeal. We're here with Scott Graybeal, CEO of Caelux. And Scott, what are perovskites and how do they compare to silicon or cadmium telluride for solar?
Well, thank you very much for having me, Jay. It's a pleasure to be here on the podcast. Perovskites are a special class of nanomaterials that, when processed under the right conditions, make very low cost yet very powerful solar cells. And if you were to compare it to silicon, silicon is actually taking quartzite, turning it into a molten material that then is transformed into wafers that then undergo significant processing steps and take quite a bit of energy to produce in order to make solar cells. And cadmium telluride, of course, is the benchmark thin film technology where you have companies like First Solar and Toledo Solar have really been major players in that market, especially First Solar. And that is a different material system. So perovskites and cadmium telluride share the fact that they're both thin film materials.
So looking at perovskites, they no doubt have the efficiency benefits, but why are we just now hearing about them for solar?
I think they're just now becoming more popular. There's been a lot of work on them because of the advancements. You know, we used to measure lifetimes of these materials in terms of minutes, maybe even seconds when they were first discovered back in 2009 as sort of an offshoot of the organic PV movement from that time frame. But the durability of these materials have improved dramatically. And now we talk about lifetimes in years, not minutes. And so now they're starting to look like something that's commercial commercially viable and it's something that can hit the market in a fairly near-term horizon. And I think that's an important feature, even though you see that the cost of silicon has plummeted and probably will continue to. Just this year alone, we've seen about a 20% price drop, quite dramatic, obviously, from where things were to where they are now. Our team in Asia points out the fact that they see module prices at sub 13 cents a watt, which is really low. But it's not the first time we've seen this. But even with that, there's still the desire amongst module manufacturers and their customers to see higher efficiency, low-cost products. And our vision is to help enhance that story more so companies can leverage our technology to apply it to their module so that they can increase the efficiency without an increase in their cost necessarily. And that's a key value proposition for how we're addressing the market.
Yeah, that's interesting that you can work with existing modules from what it sounded like. It says that you can create perovskite-only cells. Sometimes they're called single junction and what are called silicon-based tandem cells. I think that's what you mean by you're essentially augmenting silicon, right? Is there a benefit to doing one over the other?
We're focused primarily on what's called the 4-terminal hybrid tandem market. And that's just a long way to say we take the glass that customers would use in their manufacturing of a traditional solar module. We borrow it from them, we coat it, we send it back to them, and now they're able to use that glass in their production. And so what the glass is now is an active glass or a submodule. So it's a set of cells all by itself. Now, can you convert that into a single junction? Yes. The downside is the durability is not going to be quite as high as I think the industry would like to see. Clearly, there's been this push towards 25-year, even longer performance warranties, even though you maybe get some great power, but it tends to degrade faster. But if you combine it in a 4-terminal architecture, that means that our active glass top cell is independent of the silicon cell. So there's not current match, they're voltage match. So they're still in the same circuit, but they're both generating current independently. That can augment the performance of that crystalline silicon module. And so just to be clear, we don't retrofit modules. We don't take modules, take them apart, or put our stuff on the top. Eventually, we'd love to do that. But right now, we want to produce this active glass that is then integrated into the customer's module architecture. And as my friend John Bonanno likes to say, that's 2 generators in one. That's sort of how his perspective is. So think about this top glass generating current. You can think about the silicon cells that are generating current. You're adding them together prior to the point that you get out of the module. So you don't need to have a bunch of cables hanging off. We don't need 4 sets of leads. Hanging off a module comes out the same 2 leads you would normally see. They're just added together. And that is what creates this enhancement. And so what we've been able to demonstrate is about a 6% absolute efficiency uplift against traditional crystalline silicon. And that's important. That 6% translates to a lot of dollars in the pocket of somebody who builds a project with this type of technology.
Cadmium telluride is also thin film like this. Could you do something like that with CadTel, or is perovskite uniquely suited for something like that?
Well, I think that's probably a good question for solar. They're active in the perovskite space too, and maybe they're thinking about things a little bit differently. But if we were to take, let's say, just your standard cadmium telluride cell, where its best response is actually in the middle of the spectrum, I believe it's around like 1.4 electron volts. Perovskites tend to be a little higher on the spectrum. So when you match it with silicon, which is lower, you kind of end up where CadTel is today. So you get that great absorption. So I don't know if there's a lot of benefit. At least my guys say there isn't a ton of benefit to putting it with CadTel. Now, there are other thin films that it probably could work well with. We've heard CZTS as being another one that's potentially a match, but I don't think there's a ton of value, at least that we see, in matching it to CadTel per se. But the physics really lend themselves to taking what would be what we call a low band gap like silicon and a higher band gap like perovskites, put them together, you absorb more of that available sun spectrum. And this is how that becomes really kind of a winning technology. And the theoretical upper limits for this stuff is, mid 30s. So it's pretty cool that we can even approximate that today. And there's folks making devices today that are 32%.
Yeah. Now, just so everyone can be educated on this, and this is the perovskite episode. If you were just doing a perovskite only cell, it says you could go up to, say, a quadruple junction cell. And I assume that's just basically 4 layers of this, right? From what I read on that gets almost to be prohibitively expensive from a manufacturing standpoint. Is that correct?
Well, I don't know about quadruple junction, but we've definitely have a good understanding of the dual junction cells. Now, our founder, John Iannelli, he spent a good chunk of his career in multi-junction devices and 3, 4, 5 junction devices. And this was predominantly for 3-5 materials, as we call them. And that was for space applications. And you start having to have some pretty exotic interfaces between these layers in order to get them to work correctly. And I would imagine that that cost increase is likely due to those interstitial layers you have to put in. When we think about like a dual junction, you hear a lot about, tin perovskites. And hey, we're a fan. They're just not as far as long as the lead perovskites are in terms of performance and durability, but that could be an ideal bottom cell. You could make something that is a low band gap bottom cell, and you can tweak the band gap on the lead perovskite so that the two of those together are probably very powerful. So we do see that that's a potential outcome here. But our view is there is so much to be learned in the commercialization of perovskites. And I think the companies that are going to be first to market are going to carve out a fantastic niche for themselves. They're going to really be the players in terms of where we see this market growing. And that learning about how to manufacture perovskites effectively is really powerful. I think a lot of folks are spending quality time, don't want to get it wrong, in the lab and at smaller scale. But the game changes once you take this thing from a small substrate to 2 square meters. And we're having that experience today. We're doing that now. So we're having some fun.
Yeah, absolutely. Just real quick on the multi-junction. So there's more to it than you add 4 layers of glass. Are you depositioning, basically spraying on the same glass 4 times or something? What's happening?
I think in that context, you'd be depositing on the glass, let's say in a multiple junction scenario like that, on that same superstrate. We call them superstrates for our purposes, but you would be putting one on top of the other. Now, when you put them together like that, you've got to be current matched. And there's all kinds of challenges in making sure the electrons in the holes go the right direction or don't get lost in the meantime. And how thick does it have to be? Do we see a charge carrier absorption? And there's lots of challenges with that. And so that's been part of the issue. And even though you may be talking about perovskite on perovskite, there's still things to solve. We saw this in silicon, right? So when we were doing thin film silicon, when I started in the solar industry about 15 years ago, we were doing thin film silicon, and that was like amorphous silicon. It's kind of like glass, right? It's got an amorphous structure. There's no crystallinity to it. But then you put microcrystalline on it as well. And microcrystalline, turns out, had different characteristics, degradation characteristics than, let's say, amorphous did over temperature. And that caused the efficiency to actually decline over time. It may look great in the beginning, but it will decline over time. And that's what you call a series connection. And so that's why when we're going out with our solution, you can say it's a single junction approach, but it's also connected electrically in parallel. So you don't have currents flowing through the device. It's flowing across the device and out. And so that's a key difference here. So we have an anode and a cathode. The silicon has an anode and a cathode. And you basically just put them together like you're putting 2 batteries in parallel together. It's the way you think about it. And when you're doing it differently, though, you can imagine what would happen, right? You stack the batteries one after another, and you're trying to create a circuit. Well, if you got a battery that's not performing at the same level, well, it's going to become a little bit more of a resistor compared to what the others can do. It'll end up impeding the flow of current.
Yeah, that's interesting. Okay. So I wanted to also talk about what goes into perovskites. And you touched on this a little bit. You said there's organic components, and you also mentioned that you can do perovskites made out of tin and those made out of lead. You said you're using lead. So a little bit of a tough question here. How are you ensuring that lead isn't going to leach? Why the lead perovskite over tin? And how are you making people feel comfortable?
Absolutely. And look, it's something that we take seriously because we know that people are concerned about introducing lead in the environment. Any one of us who were children in the 70s know that we shouldn't eat paint chips, right? That's kind of part of the general consciousness. And we went through lots of issues with lead in gasoline, et cetera. And that was a tremendous amount of lead. There's probably 2 ways to answer this. And one way, I think, is a very scientific and biological answer, which is, okay, if this module were to leach 100% of its material into the ground, it wouldn't even get above background levels of lead. They're talking about that little lead. The thickness of these films are less than 1 micron, and the thickness of the perovskite layer is even less than a half of that. We're not talking about a lot. But let's also look at it from the standpoint of what lead is out there in industry today. I love looking at the auto industry, and I think they've done a good job with this. But there's 70 million cars that are shipped every year, and every one of them, including electric vehicles, because everybody has 12-volt displays and so forth. That's not run off of your lithium-ion batteries. That's run off of a good old-fashioned lead-acid battery. Well, every year there's 70 million cars shipped. And if you were to take and correct for the solubility difference between the lead material that's in a battery and what's in a perovskite, so the amount of lead that's shipped in 1 year, if you were to make that into perovskite solar modules, it would go back and forth to the moon 9 times. That's just how little lead. That would be about 2.5 terawatts of perovskite modules for just to be equivalent, solubility corrected, to 1 year of automobile shipments. And so folks aren't too concerned about that lead acid battery in their garage, or in some cases, multiple lead acid batteries in their garage. So that's the magnitude of the difference that we're talking about when we compare one to the next. And even then, there are still companies that are taking a belt and suspenders approach, and will definitely intersect those solutions around creating materials that will chelate lead in the event of a catastrophic failure of the module. And those are some things that will just become part of the industry norm, I imagine. And we also have part of our vision here as a traceability program, whereby our active glass is QR coded and can be traceable from the point of origin to the point of disposal.
The other thing with the perovskites is it says you're using organic components. I think it's methyl ammonia. What is it?
You'll generally see methyl ammonium iodide is one. And there's some base components I would say most companies and universities are all using. There's a fairly traditional treasure trove, a little bromine, a little chlorine, a little iodine, as well as other organic materials. And that's really where the differentiation can come into in some of these organic additives and solvent systems that you use. We've been focused on ways that we can most economically manufacture perovskites with is, I would say, the greenest solvents that we can tap into. So that's a bit of IP that we're working on. But layer on top of that, too, is the fact that this is an organometallic system, ultimately. And so those inorganic chemists out there love this. This is organometallic chemistry 101. But that's really what we're talking about, is organometallic chemistry at a very sophisticated scale. And there are a number of organic materials that are required. And so given that, that's where you have a lot of flexibility, because my organic chemists out there would love to chime in regarding the amount of flexibility there is with organic molecules. And that's very much a part of what we do. And so we have on staff organic chemists because they really understand these various additives. And then we have our physicists and material scientists understand how those additives, when incorporated in our system, can benefit the performance of the device. That's where we think that this is going to be an incredible opportunity to leverage things like machine learning, which we started early investments in a couple of years ago, to really explore the white space and continue to drive improvements in durability and efficiency on a chemistry basis. It's quite fascinating space to be in if you have any desire to be in material science or in chemistry.
Yeah, I've heard that too, about AI really helping with material science, not doing all the trial and error. About the organic components, I think that was really the thing that was holding back perovskites, is kind of this idea that it will decay over time. Have we overcome this yet, or where are we on that?
I would say that, look, there's a lot going on in durability, and I wouldn't say it's because it's based upon the use of organic materials, because gosh, some of the most permanent organic materials we have in nature are, well, organic. I mean, diamonds, for crying out loud. You would say, well, they're organic. Well, they're all carbon. Yeah, sure. When you start to really piece it together, just because something is organic doesn't mean that it's necessarily any less durable than an inorganic material would be. Given that, that really isn't the driver. I think you see that there's a lot of drivers around how these materials behave under temperature and light conditions. As an example, in the presence of oxygen, what happens? We find that a lot of the durability challenges are largely mechanical, meaning that encapsulation is extremely important. And if you can properly encapsulate a device and you've got good engineering around that, you can solve quite a few of these problems. And so that's really been our experience to date. Our team has some of the longest lifetime perovskites out in the field right now, which is fantastic. I won't get into the numbers, but they're good. In fact, we've had some feedback that are probably 3 times better than what others have been able to produce, which we're excited about that, and we want to build on that. But we can't really dismiss the impact of having a properly encapsulated device to its contribution overall to this durability challenge, and be able to make those things consistently. But that's why we're in the market, right? Because this is the new frontier, and this is where the excitement is. And if we can continue to innovate and drive this, we're pretty excited to be a part of this journey generally for the whole industry. And we have proof points out there already today, existence proofs, as we like to say, in China. There's some folks that are doing things at large scale, deploying at reasonable scales, really getting out there. And we hope to be right behind them in about 12 months and be doing something similar. We expect our first pilots to go out no later than, Q3 of next year. So we're pretty enthusiastic about where this stuff is going. And the fact that it's organic or inorganic chemistry is really kind of irrelevant.
Yeah, best I can tell, there's a Chinese company out there called Microquanta. That's the big one that's doing that right now in China.
Yeah, there's a couple, right? You got GCL and Microquanta, and there's another one called Utmo Light. They're doing great work, and we love it because every time we see an announcement from them, it gives me an opportunity to say, okay, guys, let's go get them. Let's have that conversation as a team and say, even though we're blazing a frontier, we're probably ahead in the West, but we've got competitors out there in China, and we're excited when they come out with these announcements because that gives us an indication that we're not too far behind and that this is happening. This transition is happening. We're starting to see these devices get out into the field. Microquanta, I think, has done a great job in getting various projects around. And so I take my hat off. That's great, but we're coming. We won't be too far behind.
So in August, getting more to you guys, it was announced that you received funding to help ramp up your factory as well as R&D. Your goal is to eventually, you say, produce 100 megawatts of perovskite coated glass a year, I take it. Now, look, a lot of people will think 100 megawatts is a lot, but I mean, they sometimes build 500 megawatt solar farms. So, you got to start somewhere, and 100 megawatts is probably a good enough place to start as any. So what is the plan there? What would that first 100 megawatts a year be used for, you think? Would it be commercial, industrial?
I've been in the industry long enough to remember when a 50 megawatt plant was a big deal. And, 100 megawatts was considered to be something pretty sizable. And now it's a rounding error when we see the capacity of some of the majors out there. We have customers today that have 100 gigawatts of module capacity. So it's like 0.1% of their overall capacity would be just in what we do here. For us, 100 megawatts is a pilot line. This is what we call a development fab. And so the intent for this fab is to really do two things. One is to continue to innovate and develop the technology at scale. The equipment that we have in this facility today may be changed out in 3 years as we continue to qualify new suppliers and new equipment and push that cost down. And our intent is to expand from this location radially. And so our intention is to have factories in India, in Asia, and in the US, and continue to grow that installed base as part of like a virtual factory framework where process is developed here in our location in the LA metro area. And to that extent, what we're going to be doing here, well, this factory is sold out for the first 18 months once we qualify the product. And so that's great news. So we've got a revenue stream for it. But really, the purpose of this site is not to be a cash generator. It's here to plow that back into the R&D activity. And so a good 30% of our capacity will always be focused on research and development, if not more. And the balance will be in producing products that will support customers that are more than likely local. When we start out, though, they won't be. The product will be shipping to module manufacturers overseas. But that's just because they were the first in the door. And we said, okay, we'll sign up. That'd be great. And we want to make sure that this technology gets the testing it needs and is certified by customers to then be scaled appropriately starting in like 25, 26, and 27.
Yeah, that was going to be the follow-up. Where are these first units going? And surely they're going to Asia, but there are domestic customers now, right? There are domestic silicon customers. Yeah.
There are. And when we say domestic, it's usually offshore customers that are setting up operations here in the U.S. because they've been able to generate the expertise in solar over the years. To their credit, they've done a phenomenal job. Every major, super major has announced a site here in the United States, every single one of them. So they're coming. And those are our customers here in the U.S. for the most part. And there are others, but I would say that that really represents the lion's share of that. And so when we engage with customers that are based in Asia, it's about Asia operations as well as their U.S. expansions. And we even see companies from Europe that are showing up as well.
I know that the IRA and a couple of the other bills that have passed have created a lot of incentives for building it here, being based here. And so I'm curious, are you getting those benefits manufacturing these cells here, even though the first units may be in a final product that was fabricated or manufactured overseas? How does that work?
Yeah, as long as we manufacture, it doesn't matter where the product ends up going. We're manufacturing here and creating good quality technical jobs. That's really what I think the bill is about. And it's also about investing in technology to ensure that we can operate effectively come to the 2030s with a domestic supply chain that is capable of delivering high technology, cutting edge products. And for me, this is the first time that the U.S. has really had an industrial policy supporting the renewables industry so that we can finally catch up lost ground. Many of these technologies have been developed in the United States or in the West and have found home homes outside of the United States. And it's about time we kind of figured out how to bring it back home, and so that our economy can benefit from good manufacturing jobs. And so to that extent, we are able to take advantage of it. There is a provision for a cell tax credit in the 45X tax credit scheme, which does benefit our company directly.
Yeah, that's good to know. And so where do you see Caelux going? I mean, do you see yourselves manufacturing cells end to end, or do you see yourselves kind of doing this deal where you're augmenting silicon cells with some of these bigger companies?
Well, I think that ultimately, I'm a believer that perovskites will take over. And I think as an early innovator in the scaling of perovskites, we have a place amongst that pantheon that'll eventually emerge. And I think that that's why this segment of the industry is extremely dynamic. But we have to commercialize early. I think that companies need to figure out a path to get out there at a reasonable scale so that we can incorporate those lessons learned so we're ready for that type of scale production in the future. And I think that there's probably room for both approaches, right? The 4-terminal approach supporting crystalline silicon and a thin film module that's just an exclusively perovskite module. How we fit in that ecosystem, we're going to let the market determine that. But ultimately, we're a big believer that perovskites will eventually be as durable as silicon. In the meantime, we have an approach to the market that it still adds a ton of value, and over that 25-year horizon that customers demand. But I think that we have to recognize we have to meet the technology where it is today, figure out how to scale it effectively, penetrate those markets. And from there, we're going to see, I think, a natural evolution towards maybe perovskite supplanting silicon. And that's a disruptive technology. It very well could happen. And I think if the economics support it, if the technology can meet the demands of customers, then why not?
So what are we missing here in the United States as far as manufacturing? I mean, it seems like we're getting very close to building these things end to end, but is that true? Can you totally manufacture a solar module soup to nuts in the United States today?
I think there's limited capacity from a module from soup to nuts. And I think there's a big gap when we think about polysilicon and wafering capacity when we're looking through the lens of crystalline silicon. Those are CapEx intensive endeavors. And I don't see a ton of traction. I've seen some interesting announcements out there. I see some that are looking at expansions, but really not to the extent that I think that matches what we're seeing with the crystalline silicon cell and module announcements. That does point to a future where at least that input may still have some foreign dependency to it. The challenges that I see more broadly, though, are in the next level of the supply chain. And I think that there are gaps in terms of raw material capacity across the board, where these would be raw material inputs to even crystalline silicon or perovskites, that when you start talking about the scales that you need to, multiple gigawatts, tens of gigawatts, we don't have the domestic capacity for this. Even glass has been problematic, to say the least. There are some companies that are deciding to make investments in low iron glass that allows for substantial transmission benefits over and above what you could see from, let's say, low mid iron glass, right? So there's still absorption in that red part of the spectrum that is really problematic, right? And so you tend to want to see low iron production happen. And most manufacturers of glass don't want to go down that path because, well, it turns out that the furnaces don't last as long, and that's part of the issue. And so the cost is a lot higher. So we have to kind of go to the next level of this whole conversation and say, okay, how do we get electricity as cheap as we can? Well, lots of solar is great. That's a significant part of the solution. But how do we ensure that you get the thermal capacity that you need to manufacture glass at scale so we can be in this soup to nuts arrangement such that now that you've got, let's say, less lifetime available on a furnace between maintenance intervals, now you've got to go and incorporate that into your price structure. The real question, I guess, becomes, can you do it cheaply? Can you do it to be globally competitive? And unless we can figure out the next layer of the supply chain, the answer will be no. We'll still be looking at imports for raw materials in order to make these products across the solar ecosystem, I should highlight, not just with perovskites. I think it's especially true when we think about things in the crystalline silicon space too.
Scott, I've looked at your profile. You've done this for a lot of years, and coming here and doing Caelux, it seems to me like you could have probably looked at a lot of facets like you just described of the solar industry. You could do glass, so yeah. I guess why perovskites among all of these? And just kind of wrapping up, where do you think this is all going to lead?
I think for me personally, I love the chemistry behind it. My background was in chemistry. I started off as a bench chemist. Even in the Navy, I was a ChemRadCon officer, so I definitely have an appreciation for chemistry and material science. I feel like everything I've done in my life to date has kind of pointed me at this. It's like, oh, he knows material science and chemistry, not as well as my guys do, but at least I can sit in the room room and not feel completely out of place and have the conversation around what we need to talk about. That's been great. And the business experience and doing the mergers and acquisitions that I've done over my career have been very helpful as I think about the business more strategically. Where do things go in the next couple of years? And that's something I do think about. Who are other companies that we could acquire or could partner with more effectively? Bring that into the umbrella so that we can really carve out a differentiated position and long-term sustainable competitive advantage for ourselves. And so I think all of those experiences have really rolled up, and it's been a blast for me personally.
Well, certainly looking forward to seeing what's in store for the next year for you guys. All right, Scott, I'm going to finish with a lightning round of your thoughts on different energy technologies, starting with natural gas.
Tolerable.
Crude oil.
Needed for raw materials.
Nuclear.
Big fan.
Coal. I'll add coal with carbon capture.
I really think carbon capture is an important technology for the future. I've got a friend of mine who's CEO, I think one of the most exciting carbon capture companies around, and it's amazing to hear what's happening there. Coal on its own, absolutely not a fan.
Wind.
Big fan.
Solar, you guys.
Yeah, I think solar's got a ton of potential still.
Biofuels.
I think it's a bridge. I think it's a tough place to be. With biofuels, we're going to see some really cool materials come out of biofuels. I don't think they're going to be viable as fuels in and of themselves.
Hydroelectric.
I think we're just now understanding the environmental impact of hydroelectric, and it has not been the panacea we've thought it could be.
Geothermal.
I like geothermal.
Energy storage.
Love that market. It's a heartbreak market. I think it's ripe for innovation. We've got to find a path away from traditional lithium-ion NMC cells, and I think there's a lot of good work happening out there on that front.
Energy efficiency.
Absolutely necessary.
And then finally, fusion power, nuclear fusion.
Wish them the best of luck.
All right, Scott Graybill, Caelux, thank you so much for your time.
Well, Jay, thank you very much for having me today. It was a real pleasure.
That was Scott Graybill, CEO of Caelux, a perovskite developer based in the Los Angeles area. Scott had mentioned their first customer. That would be India's Reliance New Energy. That news was first announced in 2022. I want to thank Scott for his time, as well as Kathy Berardi for setting this up. Kathy helped me with Toledo Solar and Ubiquitous Energy, two other amazing solar guests. Be sure to check out those episodes as well, 161 and 129. You can find plenty of pictures for this episode on energy-cast.com, as well as on Instagram at Host Energy and Twitter at Host Energy Cast. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 177. Be sure to join us next week when we learn how one oil and gas company is finding a more energy-efficient new way to lift hydrocarbons out of the ground. Until then, I'm Jay Downhauer. We'll see you next time.